Hello everyone, welcome to lecture 15 of this course. In the previous lecture, we discussed construction tree of a term, the subject construction theorem and construction tree of a type. Today we are going to discuss restricted lambda terms and type safe. So the motivation from studying restricted lambda terms come from the following. So we have seen that not all lambda terms are typeable in TL lambda. For example, lambda x dot xx, this is not a typeable term in TL lambda. We shall address the following questions. Is there any class of lambda terms that can be assigned types? What are the properties of typeable terms? Next, suppose there is a beta reduction from P to Q. So what are the conditions, if any, such that the types of P and Q are equal? Specifically, for the system TL lambda, we want to understand the connections between restricted lambda terms, typeable terms and type safe. So the restricted lambda terms, we are going to use the definitions and results from chapters 1 and 2 of Hindley's book Basic Simple Type Theory. So the first among these class of restricted lambda terms is called the lambda I term. I means the identity function. A lambda term P is called a lambda I term if and only if for each subterm with form lambda x dot m in P, x occurs free in M at least once. So the idea is that if you have a lambda term, we are going to look at the subterms and identify subterms of the form abstraction like lambda x dot m, and where we are going to see that x occurs free in M, that means inside M x should be there at least once, free, x occurs free in M at least once. So for example, consider the identity function lambda x dot x. So in this, this is the subterm, this is the term and this is the only subterm. So here in the body x occurs free at least once. Self application, here again the term and the subterm, they are the same thing. So this is the M, so they are occur at least one, 2 times it is occurring. Twice, so there for example this is the term, this is also the subterm. So here if we see f is occurring twice in this body, f is occurring twice. Now the subterm this part, now when you consider this subterm, so x should occur at least once, x is occurring once. So then these are all examples of the identity, this lambda I term. Now let us see these examples, lambda x dot y. So here this is the term and this is the subterm. In this M, x does not occur, but the definition says it should occur at least once. So then this is not a lambda I term. Now similarly, if we consider this is the k, that is the first function lambda f dot lambda x dot f. So here in this subterm, that is the term f occurs at least once, that is true. But once we consider this part, here M is this part, x does not occur here at least once. So then these are not lambda I terms. Now lambda I term has a nice property in the sense that if a lambda I term has a normal form, then all its subterms have a normal form as well. If lambda I term has a normal form, that means if I take all its subterms, they will also have a normal form. And interestingly, these are the terms that were originally studied by Church. He regarded the following: a term having a normal form may be viewed as meaningful. A term not having a normal form is considered meaningless. Thus, a meaningful term cannot have meaningless subterms. Now we move on to the second class of restricted lambda term, that is called BCK lambda terms. This BCK, they are all combinators that are coming from combinatory logic. So B for example stands for this abstraction, C for this and K. So the definition says that a BCK lambda term is a lambda term P such that, so earlier what we said that for each subterm of an abstraction lambda x dot of P, x should occur at least once. Now we are saying at most once, either 0 or 1. And if there is any free variable in P, it will have just one occurrence free in P. Now consider the example B. B stands for lambda x dot, so we have written in a shorthand. So it is lambda x, lambda y, lambda z dot x, y, z. This is a shorthand we have written. So here if we see as before, so x is occurring at most once. So this is here at most, x is occurring at most once. Now for this part, if we take lambda y, y occurs here at most once it is occurring. Now if you take this part, Z is occurring once. So this is a BCK lambda term. Then BCK means B will be there, C will be there, and K will be there. So C similarly lambda x, lambda x, lambda. So if you are making actually some rearrangements of this x, y, z in the body of this term. So as before it will be BCK term. Now x, y, z, lambda x, lambda. Now what about this one? Lambda x, lambda y dot x. So if I take this term, x occurs at most once, that is true. If I take this part, y should occur at most once, 0 or 1. So it is occurring 0 times. So this is okay. So in BCK they are BCK lambda terms. Now consider this function, that is also again a rearrangement, but not this way. You see, we have, it is only one occurrence. Here we have xz, yz. Now for the entire term, if I see, for example, z, if I take lambda z, so here for example, so if we change this to xz, yz, and if you concentrate only on this part, this is the m, so z occurs 2 times. So it says free, z should occur free at most once. So it is 2, so it is violated. So hence it is not a lambda, BCK lambda term. Similarly for the y combinator, if you take this as a subterm, y occurring twice, and hence y is not a BCK lambda term. Now the third one is called the BCI lambda term. Now the definition is quite similar. Now we have, so first one we had I, lambda I term, it was at least once. Then for this condition we had at most. Now it is exactly once. And the second condition is the same as before. That means this BCI lambda term means it has to be a lambda I term, and it is to be a BCK lambda term. If that be the case, then all such terms will be BCI lambda term. Note that K is a lambda I term, is not a lambda I term. K is not a lambda I term, but is a BCK lambda term. Hence it is not a BCI lambda term. And these names of these combinators, they are from the standard combinators in combinatorial logic. So these are the 3 classes that are there in restricted lambda terms. Now we will look at some properties of these restricted class of lambda terms. So let us consider a term m. M can be either any one of these. So it is a lambda I term or a BCI lambda term or BCK lambda term. So this lemma says M is closed under beta eta reduction. Now beta eta reduction means either you take a beta reduction or an eta reduction. So that means if M is a BCI, for example, if M we take as a BCI lambda term, then we make a beta eta reduction and we obtain M prime, then M prime is also a BCI lambda term. The same is true for the other classes like lambda I, BCK lambda. So this is the meaning of closed under beta eta reduction. Now we give a definition of what we meaning of cancellation of a term of the application of duplication. So consider a beta contraction. So where we have lambda x dot mn, so that means this abstraction is applied to n. So when you do beta contraction, what we get, the definition says that in the body of M, all free occurrences of x will be replaced by n. Now this is said to cancel n if and only if x does not occur free in M. That means if x, as we have seen many examples, like lambda x dot true, so if I make M is true, then x does not occur here. If that be the case, n has no role. So n is called cancelled. So we say that it is said to cancel n. When it will going to cancel n? If and only if x does not occur free in M. That means there is no occurrence, no free occurrence of x in M. That means it is going to cancel this n. Now we define that similarly if we have a contraction like this one. Now the contraction is said to duplicate n if and only if x have at least 2 free occurrences in M. That means if we have like lambda x dot xx. Now if you substitute x with n, then we are going to get n, 2 times you are going to get. That means at least 2 free occurrences of x in M, then it is going to duplicate. So what is the effect of duplication or cancellation? We are going to see. So beta reduction is non-duplicating if and only if none of its contractions duplicates. It is very important, note that none of its constructions duplicates, and it is non-cancelling if and only if none cancels. So thus there is a lemma that says that every beta reduction of a lambda I term is non-cancelling, because in a lambda I term there is at least one occurrence of x. In that condition, one occurrence, at least one. And in BCK it is at most one. So that means there will be no duplication, and BC chi is a both. So that means it is non-cancelling and non-duplicating. This is a nice result. So we are going to use BCI later on. Okay, now we consider the subject deduction theorem. If P has a type tau, we can think of P as safe. Recall that the properties of a good type system are soundness, progress, and preservation. This notion of preservation is formalized in the following theorem called the subject deduction theorem. So it says that if there is a deduction of a term P that has type tau in the context gamma in TL lambda and P beta eta reduces to Q, then there will also be a deduction of Q with P will have type tau and in the same context gamma. To put it very simply, that means if we can make a deduction of P has type tau and P there is a reduction from P to Q, then the type is preserved in the sense the type of Q will be the same as that of P. This means type is preserved by beta eta reduction. So we take some examples. So let us say P is equal to lambda x dot x P. That means the identity function is applied to 5. Now say x is of type int. So lambda x dot x type will be int arrow int. So that is of the form sigma arrow tau. Because it is application, so we have to apply arrow e. So it is sigma arrow rho, and here sigma is of type int, that is rho. So these two matches. So hence the type of P will be int arrow int, and int is consumed, so we are going to get int. Now P arrow beta reduction of P will give us 5. Of type of 5 is int. So what we have, P and Q, they have the same type. That means when P beta reduces to Q, if type of P is tau, then the type of Q is also tau. This is what the theorem says, and this is what the example also through which we have illustrated. Now consider another example where we have P as lambda x dot lambda y dot x plus y, and it is applied to 3. Again x is int, y is int. So when we apply, so this whole function has type int arrow int arrow int. There are two variables, it will be int arrow int, x plus y gives int. 3 is int. So by arrow e, it will be int arrow int. This is sigma. This part is sigma. So rho is going to be the return type. So we are going to type of P will be int arrow int. Now let us apply beta reduction of P. Beta reduction of apply will give x will be substituted with 3. So we are going to get lambda y dot 3 plus y. Now this is int. 3 plus y is int. So this will be int arrow int. So here again we find P and Q, they are of the same type. This is subject reduction theorem. Now what is the implication of the theorem? The type of a term is stable in the sense, we call stable in the sense is preserved, that remains same under this beta eta reduction. This is what guarantees type safety. So when we say type safe, it means that if a program type checks, its evaluation will never break the typing. That means it had a type tau, we are making beta eta reduction, the type will remain the same. That is what we mean by type safe. Now this theorem says that type is preserved under beta eta reduction. Can we have a reverse of this theorem? So the reverse of the theorem idea would be, we have P, we have a beta reduction, we get Q, and we are saying types are preserved. This is subject reduction theorem. The reverse means that there is a beta reduction from P to Q. Now Q, let's say, has a type tau. Here the starting point P was having type tau. We say let P has type tau. When we are having a beta reduction, then we are saying Q will also, the type of Q will also be tau. Now we are moving in the other direction. That means now we are moving this way from Q to P. We are saying, suppose there is a reduction from P to Q and Q has type tau. This part is there with us. Now we are saying whether P will also have type tau or not. This is what the reverse of the subject reduction theorem. That means if we just change the if part, the conditions if we change, then we are going to get this, that if there is a deduction of Q has type tau in TL lambda with context gamma, and there is a beta eta reduction from P to Q, so then there is a deduction of this P has type tau in T lambda. This is the literal changes that we made. But now let us examine whether it will work or not. So consider this example that with P is of this kind, lambda x dot true, and it is applied to lambda y dot y true. So let x be of type int, y be of type bool. Then this let q be true. So now when we do beta reduction, because it is cancelling, so the beta reduction will be q and it is of type bool. That means q has type bool. Now we want to say what will be the type of p. Now type of p is this part is int arrow bool and this part is lambda y dot y true. That means this is bool arrow bool and true. From bool arrow bool and bool we are going to get bool. Why? This is bool arrow bool and this is bool. This is apply arrow e. So we are going to get bool. So this is the type of this part. Now when you are applying this to this, that means this bool that we have colored red, this should match with this for arrow e. Arrow e is this is sigma, this is rho. So this is sigma, this should match. So they are not matching. Int and bool are of type different types. So hence arrow e fails. So hence p does not have a type in T lambda. That means although q has a type bool and there is a beta reduction from p to q, p is not typeable in T lambda. That means the informal statement that we made that is not true. So now the question is whether it will work from some restricted class of lambda terms that we have studied. The answer is yes. So we need to then modify the condition of the theorem. So what it says, if there is a deduction of q has type tau for some context gamma in T lambda and there is a beta reduction from p to q by non-duplicating and non-cancelling contractions, then there is a reduction of p has type tau with the same context gamma in T lambda. So this is what the addition we have done. So the thing is we are saying that this contraction is not arbitrary reduction, but it has a something special. It cannot be non-duplicating. It cannot be duplicating. It cannot be cancelling. If that be the case, then we are going to, when we moving from q to p, it will be ensured that p will also have the same type as that of q. So for example, what happened in the previous example, here in this term it is a cancelling term because x is not occurring here, so it is called cancelling, and this was the reason why p was not having type for this reduction. If this was not the case and not cancelling, then p will have the same type as q. Now how to guarantee this? So for example, when you have studied this BCI lambda term, it says that it is exactly once. That means there will be no cancellation and there will be no duplication. So BCI lambda term is one class of lambda term. That means if p is a closed BCI lambda term and p from p to q there is a beta reduction, then there is a deduction of p of the same type tau. P will have the same type as that of q if and only if there is a deduction of q. If there is a deduction of q, there will be a deduction of p as well with the same type tau. This is what we are getting from this theorem. So then when we are moving from subject reduction to subject expansion, so when we are moving from q to p, then if p is also of type tau, then we have to put some more extra constraints on that reduction. Some special kind of contractions only will allow this to happen. Preservation, we want this when we are expansion, that means we are moving from q to p, then we need some extra things. And if we are asking the question when this will be true, so we should consider BCI lambda term, this is guaranteed and we are going to get the same type of p and q under this. So recall that if a term m has a type tau, then we call it as safe. So safety means informally that a term m has a type tau that coincides with safety. That is what we mean by safety. Now let us define types of m. So we say if m is closed, so we define types of m to be the set of all tau such that there is a deduction of m has tau in T lambda, the context is empty. So that means the types of m is either empty, that means that it is untypable, or if it is typeable, there are infinitely many types. Now let P be a closed lambda term, then if we have a reduction from P to Q, it implies that types of P will be a subset of types of Q. And second, if there is a reduction from P to Q, beta reduction from P to Q, by a non-cancelling and non-duplicating reduction, then these types of P and Q will be same. Now this is coming from subject expansion theorem, the second one. But the first one, it is a general, that means this reduction is not necessarily be a it can be arbitrary reduction. Then in that case, we said types of P will always be a subset of types of Q. So informally, let us see the examples. From the examples 1 and 2, we have found that in these two cases, when we are making a reduction from P to Q, types of P and Q, they were same. But in the last example, we found that although Q has a type, P is not typeable. That means there was a reduction from P to Q. Q has a type, but P is not having any type. So that means this set is empty. The empty set is subset of any set. So that means this subset equal to we are having, and also it is a subset condition is also true. Combining, we get that types of P in general will be subset equal to types of Q. And when we have some constraints on this reduction, then these types will be same. That is by non-cancelling and non-duplicating reduction. Next, we give a definition for typeable. A term M is called TA lambda typeable. So we are in the system TA lambda. So a term M is called typeable if and only if there exists a context gamma and a type tau such that there is a deduction of this formula gamma m tau. Next, the lemma, this gives the property of TA lambda terms. The class of all TA lambda typeable terms is closed under the following operations. So number one, it is saying taking subterms. That means if I take a lambda term m and I consider a subterm of this term, then if a subterm of a typeable term will be typeable. That means if the term is typeable, each subterm is also typeable, which is what condition 1 is saying. Now why condition 1 is true, how are you going to get it? Recall that we did a subject construction theorem. So subject construction theorem, when we said that the subterms is what, if you recall the tree that we obtained, the deduction that we obtained, there all the subterms are also deductible. Hence, if a term is typeable, all its subterms will be deductible, will be typeable. Next is the beta eta reduction. That means if the term is typeable, that means if we do a beta eta reduction on the term, then that P beta eta reduction goes to Q, then Q is also typeable. Now this is by the subject reduction theorem. This is coming from the subject reduction theorem that we studied earlier. Next is it is closed under non-cancelling and non-duplicating expansion. So this is the condition that we imposed there earlier. So there by subject expansion theorem then, so it is from Q is given, we have to find the type of P. So the constant that we have is non-cancelling and non-duplicating expansion. So subject expansion theorem gives us this part, that this will be closed. And then last one is lambda abstraction. If M is typeable, then if we take the abstraction lambda x dot n, this is also typeable. Now this is coming from the arrow I rule. Arrow I is the arrow introduction rule of TA lambda. So therefrom we are getting it is typeable. So we need to remember that these are the nice properties of TA lambda typeable terms, and they are closed under these operations. So taking subterms, beta eta reduction, non-cancelling and non-duplicating expansion, and lambda abstraction. Now this theorem says the class of all TA lambda typeable terms is decidable. That means there is an algorithm that decides whether a given lambda term is typeable in TA lambda. So the proof is the principal type algorithm that we are going to discuss in the lecture 17. That means the idea about this one is if we take a lambda term m and whether it has a type tau. So we are asking whether it has some type tau. It is typeable, that means there will be a type. If it is typeable, there will be some type tau. And if it is not typeable, then we say this is not typeable. This sort of yes no answer we are going to ask for a lambda term m. So given a lambda term, we are going to have is it typeable or not. So for example, lambda x dot xx, so the answer should be no. So there is a nice algorithm called the principal type algorithm, and we are going to discuss this later. Now we have two normalization theorems. So the first one is called the weak normalization theorem. It says that every T A lambda typeable term has both a beta normal form and a beta eta normal form. Beta normal form means a normal form where no further beta reductions are possible, and beta eta normal form means it is a normal form where neither beta reduction is possible nor eta reduction is possible. This is the that means if the lambda term is typeable, every Ta lambda, if the lambda term is typeable, then it will either has both a beta normal form as well as a beta eta normal form. Now the strong normalization theorem says if m is a Ta lambda typeable term, then every beta eta reduction that starts at m is finite. That means if m is a beta Ta lambda typeable term, if m has type tau, some type, then we are doing a beta eta reduction on m. Whatever beta reduction we do on m, so this is going to, it is finite. That means after some finite number of reductions, it is going to come to some point, say m prime. So this is the strong normalization theorem. Now, so that means this second one, it is strong because this Sn theorem implies the Wn theorem. If it is going to be, if it is always terminating, that means what, there is at this point there will be no further reductions possible, whether it is beta reduction or beta eta reduction. That means it has both a beta normal form and beta. So Wsn implies Wn. So that is why it is called strong and this is called weak. Now let us consider the strong normalization theorem. It says that if it is typeable, then every beta eta reduction, this is beta, will be finite. This is finite. The number of steps from m to m prime, that is finite. Now if you take the contrapositive of this statement, that means if we do not have any finite reduction, that means they are all infinite reductions, then this term m is not typeable. So if we take this term SA is self application lambda x dot xx, SA is lambda x dot xx. So if you do this SA, so we know SA has infinite reductions. It is SA beta reduction will be SA. So the infinite reduction is there. So that means this negation of this part is true. The negation of this part should be true as well. That means m is not typeable, and we know that this term is not typeable in T A lambda, and this is we obtained from the Sn theorem. So what these theorems are telling, Sn and Wn, they provides a safety feature of the type theory. So let us view reduction as a process of computing a value. Now Wn says continue the computation until a value is reached. That means normal form. Normal form means value is reached. And Sn says all computations terminate. So this is the idea about this Sn normalization and Sn Wn theorems. That means in terms of lambda calculus, when we are introducing types, so the normal forms suggest that these computations, that means the reductions, they are going to terminate. This is then, if we translate to Turing machines, so the class of functions that are computable by Turing machines, that is that they are going to terminate. Turing machine is going to terminate. The same thing is happening here. This is the class where it is going to terminate. That normalization. That means if it is a typeable, if it is typeable, then it will have a normal form. And then that means if the terms are having normal form, we are going to have finite. After finite number of steps, it is going to stop. The computation stops there. Now, if we see the lambda restricted terms, then among these three restricted terms, the BCK lambda term, the class, every BCK lambda term is typeable. This is the theorem that we have obtained here. Now, this was given by Hindley, Roger Hindley. That is why we studied those different classes of lambda terms. And this theorem was again proved by Turing 1942. It was also proved by Curry and Fez in 1958 independently. And it is considered that and then Sn theorem was also proved by Sanchez and Diller. So the proof of Turing is considered to be simpler than any of the proofs of Sn theorem. And moreover, for Most applications of normalizations turn out to be of Wn rather than Sn. Thus, we are now arrived at the position where we can answer the questions that we started with. So, we started with this question that is there any class of lambda terms that can be assigned types? So, the answer is BCK lambda term is that class. Every BCK lambda term is typeable. So, it can be assigned types. That is coming from theorem 2. So, this we have got the BCK lambda term as the answer. Now, what are the properties of typeable terms in TL lambda? So, they are closed under different operations that we have seen. The typeable terms, the decidable, typeable terms of normal forms and termination, they will terminate. That is coming from closed under different operations coming from theorem 1. Decidable is coming from lemma 4 and normal form termination coming from WN theorems. Next, we said that if there is a reduction, beta reduction from P to Q, what are the conditions, if any, such that the types will be same? So, the condition is that it has to be non-cancelling and non-duplicating. Example, if it is a BCI lambda, then this is indeed true, and this is coming from subject expansion theorem. So, this answer 2 we have. This is the answer that BCI lambda term is one such class and the condition is this. Thus, for the system TL lambda, we can now see the connections between these restricted lambda terms, typeable terms and type safe. So, with this we conclude this talk, and to summarize today's lecture, we have studied restricted lambda terms, different classes of lambda terms, and we have studied type safe, that is typability in TL lambda. And you are requested to please see chapter 1 and 2 of Roger Henley's Basic Simple Type Theory book. Thank you for your kind attention.